Last video, Markov and Chebyshev bounded a tail using one moment, then two. This video spends everything. First, we run the Chebyshev template with an exponential dominating function, and the moment generating function we just built turns into a tail bound. Then we notice we hold a whole family of bounds, one for every rate, and optimize to reach the celebrated Chernoff bound. Next, a change of key. Convex functions sit above their tangent lines, and that single picture proves Jensen's inequality, the reason averages and curved functions never commute. We want the right tail, the probability that x is at least a. The last video taught the recipe. Write the probability as the expectation of an indicator, then dominate that indicator by a function whose expectation you can compute. Here is the indicator of the interval from a to infinity, 0 on the left, then a step up to 1 at a. This time, dominate it with an exponential, e to the s times x minus a for some positive rate s. At x equals a, the curve passes through 1 exactly, and it only grows from there, so it sits above the step everywhere. In the language of the Chebyshev inequality, the function h of x is e to the sx, the set s is the interval from a to infinity, and the infimum of h over s is e to the sa. Divide through, and the tail is at most e to the minus sa times the expectation of e to the sx. Look closely at that last factor. It is the moment-generating function of x, evaluated at s, the function we built and told you to keep in your pocket. Markov spent 1 moment, Chebyshev spent 2. This construction spends the entire catalog at once. Nothing forced our choice of rate. Every positive s gives an exponential pin to the point a, 1, and every one of them dominates the step. A shallow curve for small s, a steeper one hugging the corner as s grows. Each member of the family certifies its own bound, e to the minus sa times mx of s. So we hold not one bound, but a dial's worth, and you have rehearsed this move. For the Cantelli inequality, we tuned a quadratic's offset and kept the minimum. Same move, sharper weapon. As s varies, the bound value traces a curve, and we slide down to its lowest point. Taking the best member of the family gives the Chernoff bound. The probability that x is at least a is at most the infimum over positive s of e to the minus sa times mx of s. Which rate wins depends on the distribution of x and on a, and that is why the bound carries the search inside it. Read the chapter's ledger. Markov paid 1 moment, Chebyshev paid a second, and Chernoff pays the whole moment-generating function, which is why it earns exponentially sharp tails and a central role in coding and communications. For the chapter's last inequality, change key entirely. No dominating functions this time. The bound flows from the shape of a single function. Call g convex when its second derivative is non-negative everywhere, so the curve bends upward, like a parabola or an exponential. Draw a tangent line anywhere on such a curve and watch, the curve never dips below it. Slide the anchor point along and the picture holds everywhere. That is the claim to prove. The fundamental theorem of calculus writes g of x as g of a plus the integral of the derivative from a up to x. A non-negative second derivative makes the first derivative monotone increasing, so replacing the derivative inside the integral by its value at a can only shrink the result. What remains is the equation of a line. G of x is at least g of a plus x minus a times the slope at a. A convex curve lies above every one of its tangent lines, an inequality manufactured from curvature alone. Now let a random variable ride the tangent. The tangent bound holds at every point x, so it holds with x plugged in. G of x is at least g of a plus x minus a times the slope at a. That is an inequality between random variables, true outcome by outcome. We may pick the anchor, so pick the one point the whole chapter keeps turning to, anchor the tangent at the mean, a equals the expected value of x. Take expectations on both sides. Expectation is linear, so the slope term carries the expected value of x minus the expected value of x, and that difference is exactly 0. The linear term dies on the spot. What survives is Jensen's inequality. For convex g, the expectation of g of x is at least g of the expectation of x, provided both expectations exist. Averages in curved functions do not commute, and convexity tells you which way the inequality tips. You met an instance long ago. Take g of x equals x squared. Jensen says the second moment is at least the square of the mean, which is precisely the fact that variance is non-negative. The inequality holds even for convex functions with corners, though that proof is much harder. The smooth case is the honest one at this level. The key idea of this chapter: expectation is a bounding tool. One moment gave Markov, two gave Chebyshev, the whole generating function gave Chernoff, and Jensen needs nothing but curvature.